we are going to start talking about some motion. All right. We're going to talk about some motion. Now, what is motion? Okay, what is motion? Now, motion is an object's change in position relative to a reference point. Hey, DJ, can you mute your Zoom? There we go. All right. So the definition of motion: motion, an object's change in position relative to a reference point. Okay. So we're always looking at a reference point. All right. Now, the main reference point that we're always focused on is Earth. All right. We always use Earth as a reference point. Whenever you're walking, how do you know you're walking? Well, you see trees go by you. You see a fence go by you. You see cars go by you. Whenever you're driving, how do you know you're moving? Okay. How do we know we're moving? Okay. Now, motion is often described in a direction and distance. Okay. Motion is often described in a direction, so I'm going 3 feet forwards. Okay. So it's always described with a direction and a distance. Okay. Now, if you think it's easier if you could pin my screen, that might be easier on a Google Meet. It's up to you guys. Okay, so that's motion. Motion is an object's change in position relative to a reference point, and it usually has direction and distance. So a reference frame, okay? I just said it's what we use to determine if an object's moving or not, okay? And the main reference point is Earth, okay? So reference frame is to observe whether or not an object is in motion, okay? Must be compared to a stationary object within a reference frame. Okay. It must be compared to a stationary object within a reference frame. So I actually have an example video here. So we're going to check out these two cars. We're going to check out these two cars, and we're going to see if we can see which one's moving. Well, clearly the van was a lot faster. The car is still back. All right, so the reference point here was how large the vehicle got. But when he goes to the air, this is where it actually gets a little interesting. Sitting still, we can tell that both cars are moving, and especially the gray car is moving a lot faster, right? We can see the gray car is moving a lot faster. However, in this next clip, the drone moves as well. And when we see the drone moving, the car looks like it's in place. If you focus directly on the car, this black car, it looks like it's not moving. If you focus in on that car, looks like it's not moving. However, with our reference frame, we can see Earth. We can see the lines of Earth below it, and that's what tells us it's moving. That's what a frame of reference is. Okay? That's a frame of reference. So now we're going to talk about the difference between distance and displacement. Now, I know you guys already know distance. All right? Distance is the measure of the path taken. All right, how far did you go? Okay. where displacement is the change in position from the start to the end point. From the start to the end point. Okay? I have a little picture here. Okay? So if we start here and we go on the path, that's our distance. All right? It's the measure of the path taken. Whereas displacement is the change in position from the start to the end. So if we look from here to here, that's our displacement. Okay? All right. You don't need to write that last part. Okay? The key thing, displacement, once again, we're always focused on direction. Displacement must be in a particular direction. I would write that down. Displacement must be in a particular direction. So if we look at this displacement, the displacement is actually southeast, right? Southeast of where we started from. So displacement must be in a particular direction. So I got an example here. All right, it's kind of a complex example, but we're going to try it out. Okay. So Jim, this is Jim's house. We got Cindy's house, the grocery store, and a red penguin. Okay. Jim's mom tells Jim to go buy some eggs at the grocery store. On his way, Jim sees and walks up to a red penguin 50 meters right of the grocery store. He's so excited about the eggs, he runs to Cindy's house to tell her about this. Then Jim gets a call from his mom asking about the eggs. He rushes to go to the grocery store before it closes, but as soon as he gets there, Jim passes out. What is Jim's displacement? Okay, so what I'm going to try here is, here we go. So it says, what is Jim's displacement? Well, if he started at Jim's house, displacement is start to finish. Okay, so if we started there and he finished at the grocery store, what's the displacement? So how far is Jim's house to the grocery store? Well, the displacement should be 200. Okay. Then it says, what is x? Okay, well, this requires a little bit of thinking. All right, so we know Cindy's house is here. That's Cindy. Okay, and we know that red penguin was over here. Oh, I'm not good at drawing. There's my penguin. All right. And let's see. What is x? Well, we know from Cindy's house to the red penguin is 150 or 125, my bad. 125. We're trying to find Cindy's house to the grocery store. Okay, that's what we're trying to solve. And we know the grocery store to the penguin is 50. So if we know the total distance is 125, we know this distance is 50, I just got to solve for x. So what we have is 125, that's my total, minus this part right here, which is 50. That will give me x. So 125 minus 50 is 75. And 75 is your answer. Okay, 75 is your answer. What is the total distance Jim traveled? Well, all right, let's do this. So Jim walked to the grocery store, which is 200 meters. So he walked 200 meters. Then he sees and walks to a red penguin 50 meters to the right. He forgets about the eggs and runs to Cindy's house. Well, Cindy's house is 125 meters. And then he gets a call from his mom saying you have to go to the grocery store. Well, we just calculated X to be 75. So hopefully you guys have calculator. If you don't, calculator should be on my front table if you need calculators. All right. So if we check this out, that's 450. And that's his distance. So that's the biggest thing I want you guys to see is if you look at the difference, displacement was start to finish, where distance was the total distance he ran. Okay, so hopefully you kind of understand that concept. Okay. So let's check this out. Speed. So now that we know distance, we know displacement. What is speed? And speed is how fast an object moves. All right, I feel like we already know that. But we're gonna use calculations to calculate speed. And the speed equation. Oh, I guess we'll get to that on the next slide. Most often, the speed is presented as an average. Now, there's two different types of speed. If you see on the bottom, instantaneous speed is speed at a specific time. All right, so let's say you're a track runner and you start off the 100-meter dash kind of slow, right? You don't start the 100-meter dash with a fast speed. You normally end faster than you start. So the instantaneous speed changes. However, the constant speed is the amount of speed an object covering an equal distance at equal amounts of time. All right, so it's just how fast you're moving over the entire time. So that's the difference of instantaneous and constant. All right, and this is the equation. So I would write this down. All right, this is key for this activity. Tomorrow's lab, you're going to be using this quite a bit coming up. Okay, so speed is equal to distance over time. So if we check out an example, what is the average speed of an object that traveled 35 meters in 10 seconds? Well, it's pretty straightforward. If we use our equation, well, we have distance over time. So distance over time. So if we check this out, the distance is 35 meters over 10 seconds. Your answer is 3.5 meters per second. Okay. And units are key. They're very, very key when solving these. Always add the units, meters per second, because if you look at the next example, what is the average speed of a car that traveled 110 miles in 2 hours? Well, once again, distance over time. So distance over time, the average speed should have been 55 miles per hour. All right, make sure you add your units. The last one's a little tricky, okay? How many kilometers could a person travel if they had a constant speed of 5 kilometers per hour for 3 hours. So if we look at this one, it's a little different. This one's a little different. So if we look at this one, speed is equal to distance over time. Okay? Speed is equal to distance over time. So I'm given my speed. My speed is 5. I'm trying to calculate my distance, and I'm given my time is 3 hours. All right, so the opposite of division is multiplication. So I have divide by 3. I got to multiply by 3 on both sides. So I have 15 is equal to the distance. Now, what unit am I going to have? Well, it says in the question, it says how many kilometers? Well, I have 15 kilometers. And that's how you would solve that type of problem. Okay. So hopefully using this equation, it's pretty straightforward. Okay, speed is equal to distance over time. Now velocity, this is the last one, I'm pretty sure. Yeah, this is going to be the last one. Velocity, the only difference is velocity has a speed and direction. So that's key. Whenever you see a direction, that's velocity. Okay, velocity has direction. Okay, velocity has direction. All right, so the direction, it can be north, it can be south, it can be east, it can be west, it can be angle, it can be anything. All right, it's just direction. So whenever you have direction, that's velocity. You don't have to copy the second and third bullet point. I'm just giving examples out. Okay, now velocity can be two different ways. Calculate the velocity using the same equation, just as speed, just add a direction. All right, so speed, your numbers are always going to be the same. You're just going to add a direction. Okay, I am heading left. I am going right. I'm going up. I'm going down. Okay. Is there any questions on that? There's some examples, but that is it. Okay. So it's the same calculations, distance over time. However, in this case, you're adding a direction. Okay. I had some example problems, but I think we got it. I think we got it. Actually, let me look. I skipped this one. Last one. Resultant velocities. All right, this is one of my favorite examples because combining velocities to determine the overall velocity of an object. So if you're walking up in a bus, you're actually moving, let's say 1 meter per second. The bus is moving 15 meters per second. Since you're moving the same direction, you add those two. Okay, if two velocities are in the same direction, add. Whereas if you're walking to the back of a bus while the bus is driving, they're in opposite directions and you would subtract. Okay. All right. If they're going the same direction, add. If they're opposite, subtract. All right. That is all I had. Okay. So for today, I'm going to explain today's and tomorrow because tomorrow we're just going to kind of hit the ground running. For today, I posted some examples on Google Classroom. Okay. Some distance over time equals speed. Okay. Got some examples. If you would like to work with somebody on it, that's fine. I will stay on the Google Meet for the rest of the class. If you guys have any questions, you do not have to stay on the Google Meet for the rest of class. That's up to you guys. Now, tomorrow we're going to be doing a motion experiment, okay? Most likely we'll join a Google Meet real quick. I'll describe what the experiment is, and we'll be good to go. Okay, we'll do an experiment tomorrow. Wednesday, we're going to do a car lab. We're just going to see how it all goes. Okay, so I did post some examples on Google Classroom. Try to get those done. I think there's 20, but you have about 10 minutes left in class, so you should be able to get those done. All right, is there any questions? All right, well, I hope you guys have a fantastic day. Like I said, if you don't have any questions, you guys can log off and we'll be good to go.